My sincere greeting to one and all. I am Tamanna from BSc Chemistry Honours second year. Today I am here with chapter Diazomium salts. Introduction. Diazomium salt discovered by Peter Gericks in 1858 constitute a very important class of aromatic compounds having the general formula ArN2 positive X negative, where X negative may be any anion such as chlorine, Br negative, HSO4 negative, NO3 negative, BF4 negative, etc. The name diazomiums itself originated from the fact that these compounds contain two nitrogen atoms. French azote means nitrogen and resembles ammonium salt in certain respects. In if it may be pointed out that aliphatic diazomium salts, example, the compound having the NH2 positive, N2 positive, X negative group attached to an alkyl ra- radical, radical are too unstable to be isolated. Structure. The simplest and most important diazomium salt is benzene diazomium chloride. Let us first consider the structure of these compound as the representative of structures of diazomium salts in general. The important evidence leading to its structure may be summed up as following. First, molecular formula. Its molecular formula is C6H5N2Cl. Second, observed behavior. First, it is a colorless crystalline solid soluble in water but insoluble in organic solvents such as alcohol and ethers. Second, it undergoes ionization in aqueous solution as shown by the conductivity measurement of the solution. The benzene diazomium chloride exhibits salt-like behavior. Third, it undergoes many substitution reactions in which N2Cl group is replaced by monovalent group such as halogen, cyanide, etc. Third, fourth, it undergoes coupling reaction to form azo compounds such as para-hydroxyazobenzene. Fifth, on reduction with stannous chloride and hydrochloric acid, it is reduced to phenylhydrazine C6H5NH2. Sixth, in alkaline solution, it forms salt known as diazoates, which exhibits geometrical isomerism and exhibit in synosis and anti or transforms. Third, earlier formula. A. Grease's formula. The earliest structural formula for a benzene diazobium chloride was suggested by its discoverer Peter Gierks. In this formula, the two nitrogen atoms were directly attached to benzene nucleus as shown below. However, this formula was immediately rejected as it could not account for the following properties of benzene diazobium chloride. First, its salt-like character. Second, it reduces to phenylhydrazine, which contains only one nitrogen directly attached to benzene nucleus. Third, the displacement of N2Cl group as a whole in most of the reactions. Fourth, the formation of azo compounds in coupling reaction. B. Kekulé formula. Kekulev proposed the following structures in which only one nitrogen is directly attached to benzene. This formula could explain most of the reactions of benzene diazomium chloride, but it failed to account for first, salt-like behavior of benzene diazomium chloride. Second, instability of benzene diazomium chloride as compared to azo compounds since both contains N double bond N leakage. C. Blomstrand formula and its modified form. Blomstrand suggests the following structure for benzene diazomium chloride. This structure has now been modified as supporting evidence is the above ionic structure, which is comparably to that ammonium chloride H single bond N triple bond H3 Cl negative, is supported by the following observations. First, benzene diazomium chloride is soluble in water but not in organic solvents due to its salt-like structure. Second, the conductivity of aqueous solution confirms the presence of charged structures. Third, IR spectrum shows the presence of nitrogen triple bond. Fourth, it can explain all the reactions of benzene diazomium chloride. Fifth, it can explain the existence of geometric isomers of diazonates. It has been suggested that in the presence of hydroxide ion, the diazobium ion exists in equilibrium with diazohydroxide, an unionized compound, and the salt derived from it as shown below. Diazomium chloride gives diazomium hydroxide, diazohydroxide, sodium diazoacetate. The concentration of the different species depend on the pH of the solution. In acid solution, the equilibria favors the diazobium ion, which in alkaline solution, the equilibria are in favor of the diazoates. The diazoates can naturally exhibit geometrical isomerism and exist in syn or cis and anti or trans forms as depicted below. Syn or cis diazoexate, anti or trans diazoacetate. Nomenclature. Diazobium salts are named by attaching the word diazobium to the name of the parent aromatic compound. This is followed by the name of the anion. For example, benzene diazobium chloride, para-nitrobenzene, benzene diazobium hydrogen sulfate, para-toluene diazobium bromide, para-chlorobenzene diazobium fluorate. Preparation of diazobium salt. Diazonization. Diazonium salts are usually prepared by the reaction between aromatic primary amines and nitrous acid obtained in situ from sodium nitrate and a mineral acid such as hydrochloric acid or sulfuric acid at about 273 to 278 Kelvin. The reaction is called diazotization, diazotization and it may be represented as primary aromatic amines with 2 moles of HX plus NaNO2 gives A diazomium salt plus NaX plus 2 moles of H2O. Procedure of diazotization. For carrying out diazotization, the amine is dissolved or suspended in an aqueous solution of mineral acid and the resulting solution is cooled at about 273 Kelvin. A well cooled aqueous solution of sodium nitrate is then added slowly, taking care that the temperature of the reaction mixture does not rise above 278 to 283 Kelvin. If the temperature is allowed to rise higher, the diazobium salt formed get converted into phenol. The addition of sodium nitrate solution is stopped as soon as few drops of the reaction mixture give a blue color with starch potassium iodide paper indicating the presence of some unreactive nitrous acid in the reaction mixture. In other words, it shows the completion of diazotization. Since excess nitrous acid is likely to interfere with the subsequent reaction of diazobium salt, it is destroyed by the addition of a small quantity of urea, and any urea left unreacted does not interfere with the reaction of diazobium salt. The above solution containing the diazomium salt is used as such for the other reactions and no attempt is made to isolate the pure salt. This is because diazomium salt often undergo explosive spontaneous decomposition. Furthermore, since diazomium salt decomposes slowly even in cold solution, the solution must be used for further reaction immediately after preparing. It may be pointed out that liberation of nitrous acid for sodium nitrate or formation of diazomium salts required 2 moles of the mineral acid per mole of amine to be diazotated, but in actual practice the amount of acid used is about 3 mole. The use of excess acid is necessary to maintain proper acidity of the reaction and to prevent the combination of diazobium salt with the undiazotized amine. Precautions to be taken. During the preparation of diazomium salts, the following precautions should be taken. First, the temperature must be carefully controlled and not allowed to rise above 283 Kelvin. Otherwise, a phenol would be obtained. Second, the mineral acids such as HCl or H2SO4 should be used in excess. Otherwise, diazobium salt formed would combine with undiazotized amine. Third, excess of nitrous acid must be destroyed. Fourth, never try to prepare pure dry salt because it is highly unstable and undergo explosive decomposition. Mechanism of diazotization. It has been shown by Larkworthy 1956 that the actual mechanism of digestion depend upon the extent of acidity and the concentration of reactants. But there is no doubt that the nucleophilic amine undergoes attack by some electrophilic species such as nitrosium ions NO positive or nitrous anhydride N2O3 obtained from nitrous acid. Thus, one of the probable mechanism which appears to operate in many cases may be summed up as follows. In the presence of strong acid, nitrous acid dissociated to give nitrosinium ion. This ion attacks the nitrogen of the amine to form an unstable and nitroso ammonia ion intermediate. The intermediate immediately loses a proton to form an N-nitrosoamine. This in turn undergo a rearrangement by a proton shift, similarly to ketoenol tautomerism, to form diazohydroxide. Finally, the presence of acid, the diazohydroxide loses water to form the diazomium salt. The complete mechanism is summed up as follows: nitrous acid, then nitrosamine ion. The mechanism is shown. Aromatic amine carrying electron withdrawing substituents such as NO2 on the ring are rather different from diazoestes. This is because the electron withdrawing substituent reduces the nucleophilic character of nitrogen of the amine and thus renders it less susceptible to attack by electrophilic species. This observation also consists evidences in favor of the above mechanism. Diazonium salt containing anions such as Bf4 negative are generally obtained from more common diazonium salts on below. Physical properties. First, diazomium salts are generally colorless crystalline solids freely soluble in water. Second, they are seldom isolated because of their instability and explosive nature. Third, with certain metallic salts such as zinc chloride, diazomium salts form double salts ArN2 positive, ZnCl4 2 negative, which are quite stable. Chemical properties. Diazomium salts are highly reactive compounds and are extremely useful as intermediates in the preparation of many aromatic compounds. By the use of diazomium salts as an intermediate, it is possible to introduce onto the aromatic ring substituent which are difficult or impossible to introduce possibly to introduce by other methods. In addition, it is also possible to introduce substituent in positions not favored otherwise in direct process. The reaction of diazomium salts may be divided into two main types. These are A. Reactions in which N2 is given out and the diazomium group is replaced by some other atom or group. B. Coupling reaction in which the nitrogen atom are retained in the product. As, as already stated, diazomium salts are employed by various reactions in the form of their aqueous solutions, which are prepared just before they are required to be used. The important reaction of diazomium salts are discussed below. Reactions in which nitrogen is lost as N2 and the diazonium group is replaced by some other atom or group. First, replacement by chlorine, bromine or CN. Sandmeyer reaction. A very important reaction of diazomium salts is the Sandmeyer reaction, in which the diazomium group is replaced by a chlorine or bromine atom or a cyanide group. This reaction this reaction is carried out by treating solution of freshly prepared diazomium salt with cuprous chloride, bromide or cyanide. Thus we have the following reaction. For example, para-toluene diazomium chlorides give para-chlorotoluene in presence of CuCl. In this case of replacement of cyanide, the diazomium salt solution is neutralized by sodium carbonate before being treated with cuprous cyanide. This is to prevent the loss of cyanide as HCN. Mechanism. The mechanism of Sandmeyer reaction is uncertain. However, a probable mechanism involving free radical may be summed up as follow by considering the reaction with cuprous chloride. It appears that species such as CuCl2 negative, CuBr2 negative, and CuCN2 negative are first formed with which subsequently loses an electron to diazomium ion to yield an aryl radical, cupric salt and nitrogen. The aryl radical and cupric salt ultimately react to give the final product. Gutterman reaction. It is modified procedure known as Gutterman reaction. The replacement of Cl, Br and Cn is carried out by using copper powder and halogen acid by or potassium cyanide in place of cuprous cyanide, that is Ar2 positive X negatives. First in reaction with copper plus HCl gives ArCl plus N2. Copper plus HBr gives ArBr plus N2, and same with copper plus KCN gives ArCN plus N2. Ultimately reacts to give the final product. Gutterman reaction. In a modified procedure known as Gutterman reaction, the replacement of chlorine, bromine, or CN is carried out by using copper powder or halogen acid or potassium cyanide in place of cuprous cyanide. This is given below. Synthetic utility. Sandmeyer or Gutterman reaction offers a very useful method for preparing aryl chlorides and bromides in pure form. This method is preferred to direct halogenation as the latter usually result in the formation of mixture of products. Since the cyanide obtained by the above process can be easily hydrolyzed to carboxylic acid, then substituent a good method for preparing aromatic acids. For example, orthotoluic acid may be prepared from toluene as follows. Toluene react with with presence of HNO3 plus H2SO4 give orthonitrotoluene. Then H positive ions give orthotoluenide. Then in presence of NaNO2 and HCl gives orthotoluene diazomium chloride. Further with reaction with CuCN give orthotolonitrile. Further on hydrolysis gives orthotolic acid. Second, replacement by iodine. Replacement of diazomium salt group diazonium group by iodine can be brought about merely by warming the diazomium salt solution with potassium iodide solution. Mechanism. The reactions proceed by SN2 mechanism. I negative ion being the attacking species and constitute the best method for introducing iodine onto the aromatic ring. Third, replacement by fluorine. Bales-Sitzman reaction. For replacing the diazomium group by fluorine, the diazomium salt solution is treated with fluoboric acid HbF4, which dissociation fluorate Ar2 positive BF4 negative get precipitated. The precipitate is filtered, washed and dried to isolate the fluoro fluorobroate. Diazomium fluorobroates are relatively stable compounds. The Dry salt of heating decomposes yields to the aryl fluorides, boron trifluoride, and nitrogen. The reaction is known as Bell-Sussman reaction. It may be depicted as follows: diazobium salt plus HBF4 gives insoluble ArN2 positive BF4 negative plus HX. Mechanism: the reaction proceed by SN1 mechanism as shown below. Fourth, replacement by OH. On warming an aqueous solution of the diazobium salt, the diazobium group is readily replaced by OH to yield a phenol. For example, diazobium salt plus H2O gives phenol plus N2 plus HX. Mechanism: the reaction is followed by SN1 mechanism as shown below. The first step will be very slow step which leads to the formation of a carbocation plus N2. Further react with water, it will give phenol. The F14 reaction take place slowly even on allowing an ice cold solution of diazobium salt to stand. That is why diazobium salt solutions are usually further reaction intermediately after their preparation. The phenol formed in the reaction can couple with the diazobium salts to form azo compounds as discussed a little later. The coupling reaction is however suppressed in strongly acidic medium. As such, the formation of phenols is best carried out by slowly adding the diazobium salt solution to a large excess of boiling dilute sulfuric acid. Synthetic utility: the above method is very useful for preparing phenols which are otherwise difficult to obtain. For example, metabromo-phenol may be prepared from nitrobenzene as follows. Uh, Nitrophenol reacts in presence of Br2 oblique AlCl3 gives metanitro metabromo nitrobenzene. Further, the reaction will proceed to give metabromophenol. Fifth, replacement by NO2. This is carried out by decomposing diazobium fluoroates with sodium nitrate solution in the presence of copper powder. Thus, we have the following reaction. Synthetic utility: the reaction can be used for introducing nitro groups in the specific position in benzene ring. Refers to the preparation of para-dinitrobenzene from aniline, section 3.7. Sixth, replacement by aryl group. Gumbberg-Bussmann reaction. Many diazobium salts react with other aromatic compounds in alkyl solution to furnish compounds in which the diazobium group has been replaced by aryl group. For example, the given reaction is to form para-bromodiphenyl. Seventh, replacement by arsenic acid groups. ASO3H2 Burt reaction. This is carried out by decomposing a diazobium salt with sodium acetate in the presence of a copper salt. For example, the following reaction. Replacement by hydrogen. Replacement of diazobium salt group by hydrogen can be best carried out by allowing the diazobium salt solution to stand in contact with hypophosphorus acid, preferably in the presence of cuprous ions. The reaction may be represented as shown below. The reaction proceeds by a free radical mechanism as illustrated below. Diazobium salts plus H3PO2 plus H2O in presence of Cu positive gives aryl group plus H3PO3 plus N2 plus HX. The mechanism is shown below. That is why it can attack only very reactive aromatic ring. This is ring which contains strongly activating substituent. However, if the electrophilic character of diazomium ion is increased by introducing electron withdrawing substituents like NO2 into the aromatic ring of the diazomium ion, coupling may take place with even less reactive aromatic compound. Choice of experimental condition. An important factor to be taken care of in coupling reactions is the choice of suitable experimental conditions. The reaction conditions such as that coupling reaction take place rapidly and the possible side reactions such as reaction of diazomium salt with water itself to form phenol and the coupling of phenol thus produced with diazomium salt are prevented from taking place. The most important reaction condition which requires to be regulated is the pH of the reaction medium. This is illustrated below in case of coupling with phenols and tertiary amines. 10th, coupling with phenols. When treated with phenols in weakly alkaline solution, diazobium salt undergo coupling to form hydroxoazo compounds. For example, benzene diazomium chloride plus phenols in weakly alkyl medium having pH 9 to 10 gives parahydroxoazobenzene. Mechanism. The mechanism of the reaction involves the electrophilic attack of diazomium ion on the phenoxide ion as shown below. Benzene diazomium ion plus phenoxide ion gives the following azo compound. Role of pH in coupling reaction. The choice of optimum pH range of the employed in this reaction may be understood in terms of the respective equilibria involving the diazomium ion and phenoxide ion. It may be recalled that in the presence of OH negative ion, the diazobium ions occurs in equilibrium with diazohydroxide and the diazoate salt. Both diisohydroxide and diazoates are not electrophilic and therefore do not take part in coupling. This means that in strongly alkyl reaction medium high pH value, the concentration of attacking electrophilic species would be low. In other words, a high concentration of attacking reagent requires the solution to be acidic. For example, having pH very low. Phenol in aqueous solution occurs in equilibrium with phenoxide as shown below. Due to the stronger electron releasing effect of O negative, then OH phenoxide ion is more reactive toward electrophilic attack, but the equilibrium depict above the shift towards phenoxide ion only in an alkaline solution. Thus, a higher concentration of phenoxide ion requires the reaction medium to be alkaline, having pH high. In the light of above discussion, it is evident that the optimism pH range for the coupling reaction would be result a compromise. The optimum pH range of coupling of phenol has been found to be 9 to 10. This means that coupling of phenols is best carried out in slightly alkaline medium. 11. Coupling with tertiary amine. Coupling of diazomium salt with tertiary amine takes place in slightly acidic solution to form dialkyl aminoazo compounds. For example, benzene diazomium chloride plus N-dimethyl aniline in weakly acidic medium having pH 4 to 5 give paradimethyl aminobenzene plus HCl. Mechanism. The mechanism of reaction may be depicted as below. Benzene diazomium ion plus N-diazomium methyl aniline gives the compound. Role of pH. As already explained, the high concentration of diazomium ion requires the reaction medium to have a low pH value. At a low pH, the amine will be largely protonated as shown below. Now, the protonated amine, due to positive charge, is quite unreactive toward electrophilic attack. This means that in coupling reactions, the amine should be predominantly in the form which is possible only if the reaction medium has a high pH value. As a result, the compromise between the pH range requirements of diazomium ion and the free amines, the actual pH range employed in the coupling of tertiary amine is 4 to 5. Example, the reaction medium is slightly acidic. 12th, reaction with primary and secondary amines. Primary and secondary amines are generally react with diazomium salts in mildly alkaline solution to form colorless diazoamine amino compounds. In this reaction, attack of diazomium ion takes place at amino nitrogen rather than one of the ring. However, the diazoamino compound thus formed undergo rearrangement when heated in acidic medium to form colored azo compound. For example, benzene diazomium chloride plus aniline in presence of CH3COO negative give diazoaminobenzene plus HCl. Further, on reaction with H positive and heat, it give para-amino azobenzene. Synthetic applications of diazomium salt. In introducing the chemical behavior of diazomium salt, it was stated that diazomium salts can be employed as a very useful intermediate in the synthesis of a number of aromatic compounds, many of which are difficult or impossible to synthesize by other method. The preparation of acid orthotolvic acid, metabromophenol, and 1,3,5-tribromobenzene were cited as some example of synthetic utility of diazomium salts. A few more examples are given below by the way of further illustration. First, synthesis of metabromotoluene, further toluene from toluene. Toluenes on reaction with HNO3 and H2SO4 gives nitrotoluene. Then further reaction with FeH positive gain amine aminotoluene. Then further reaction with CH3CO2 O negative gives amine at and NHCOCH3. Further bromination will attach the Br and the reaction further proceed by hydrolysis and then NaNO2 oblique HCl, and lastly with reaction H3PO3 give metabromotoluene. In the above synthesis, the conversion of nitro to this constitutes the key step. It is based on the fact that NHCOCH3 is much stronger ortho-para director than CH3 group. Since the para position is already blocked, bromine is introduced at ortho position with respect to NHCOCH3 or meta position with respect to CH3. Second, synthesis of bromonitro bromobenzonitrile from nitrobenzene. Third, synthetic of 3,4,5-triiodonitrobenzene from paranitroaniline. Fourth, it it further required the nitro group may be removed from by conversion of NS2 group followed by digestion and reduction to get 1,2,3 triiodobenzene. Fourth, synthesis of metadichlorobenzene from nitrobenzene. And fifth, synthesis of para-dinitrobenzene from aniline. The mechanism of the reaction is shown below. Thank you.